speaker is Danny Wise. I'm going to talk about known growth gaps for special Q complexes.
Okay, thank you very much. Thank you for organizing this conference, inviting me here. Let's get started. On myself. So this is joint work with Jiakai Li. Let G act properly by isometries on metric space epsilon. It's there. Can you help with it? The growth function of G with respect, of course, to this action is following little counting function. It's the number of elements of length at most n. So let's say with respect to epsilon and some point b in epsilon. Okay, so let's unpack this. This is the set of elements G with the property that they translate the base point B at most n away from itself. Right? And we're just looking at the cardinality of that set. Okay? Size of the n balls from the viewpoint of epsilon. The growth rate with respect to this action is the number lambda g, which is defined to be the lim sup of the nth root of this growth function. So if you're like me and you just kind of ignore stuff like that, that just means lambda g is most efficient, I'll just say best, over estimate such that fg of n is approximately that. Okay? So we're kind of undoing all the damage that we did. Now these are ideas that appeared long ago. So for G, word hyperbolic, for example, it is known that this sequence of nth roots of balls converges. And it's from Cannon's influential early work recognizing this. And actually, say a little bit more, you could say that it's quite a good estimate for the growth function This is subsequent work of Bernard mainly. Now, of course, you realize that the growth rate.
For those statements, Danny, do you need it to be the action to be co-compact, or can you get GX in hyperbolic
Yes, thank you.
action?
That's correct. Thank you.
And is that only enforced for that note, or is that?
So, I will say, please experts correct me. If I remember correctly, this is proper co-compact for both of these. Okay. You know, some of this stuff might work for a quasi-isometric action or something like that. Quasi-isometric in that orbit. I don't care very much. Okay. The growth rate, what was it? Well, the growth rate depends, of course, on the action. So I'll just say on epsilon, but not on the point B. The growth rate won't depend on the point B, right? Because you can start imagining, you know, what's going on over here. Here, probably, I'm assuming it's action's problem. Okay, so, let me throw in a few more definitions, mostly definitions. For H in G, we will define, analogously, the growth rate of the subset H to be the same thing, except we're restricting to the elements in H. Okay, so that's the growth rate of H and the growth function of H, and then accordingly we define the growth rate of H, not the growth rate of G, but it's with respect to the action of G on epsilon. It's just going to be the same game. Okay, so was I hearing people whispering about that? Little fun? Okay. Okay, let's say a tiny bit more. Continue populating this with some simple points. Well, just a couple of stupid examples to have in mind. So free abelian group, and let's imagine it acting on its Cayley graph, right? So has and that's a good example. Is a Cayley graph, of course. Okay, you're all thinking that, I hope. So this is approximately n to the d, and so lambda ends up being 1. There's no exponential growth, and so everything kind of disappears when we take lim sup bent roots. Right. Likewise, when G has sub-exponential growth. Another example, if you take a free group acting as often the case on the universal cover of a bouquet of 2 circles, right? So you all are experts in these types of this picture. And you know why I'm having trouble drawing more and more. And if I'm not mistaken, the last time that I did the computation, I got 2 times 3 to the n plus 1 minus 1 minus 3. I do not guarantee that. Okay? But the important thing here is that, which you all know is true, right? Because you all see that, oh yeah, the ball keeps growing by a factor of 3 each time, right? Because the spherical growth rate, the growth of spheres, that's obviously tripling every time. And we know what happens over there. And so you conclude that, so lambda g over here, or lambda f2, I'll just say lambda g, I'll just say lambda. So lambda is equal to 3. Okay. On the other hand, if we used instead the universal cover of a theta graph, then, well, that looks like this. And now the growth function is approximately 2 to the n, and lambda is equal to 2. Okay? And when you're, some of you are going to get bored of me and this talk, so give you something to do. Compute f and lambda for a genus 2 surface, whatever genus you want. You broke it up into cubes. So let's break it up so that the universal cover looks like this. 5 per vertex. And you'll find it to be an enjoyable exercise that will make you fond of 2x2 matrices and linear algebra, okay, as you pursue these functions and some recursion and some eigenvalue. Okay? And it is a nice clean answer. Let's get closer to our topic, which we haven't quite arrived at yet. Mark that if H has finite index in G, so getting back to the growth rate of some subset, which is typically a subgroup, then, what you can check is that the growth rate, the growth function of this subset is greater than or equal to some constant times the growth function of the whole group, right? And of course, it's by definition less than or equal to the growth function of the whole group, and so the growth rate of H ends up being equal to the growth rate of G. So I guess I can now mention something that Dave brought up, which was Dahmani, Futer, and myself. None of this false modesty, just W, whoever that might be.
Nobody would accuse you of false noise.
Are co-authors allowed to ask questions?
Yes.
Yes? Okay, so we've set that straight from yesterday.
That wasn't a question.
Saul, you have one remaining comment to make. Okay. Let each bit of a giddy audience this morning. I guess it wasn't hot enough last night. Let each be a quasi-convex subgroup of word hyperbolic G. Then the growth rate of H, infinite index, very important, obviously, because of the previous statement. Then the growth rate of H is strictly less than the growth rate of G. Just a second, let H be an infinite index quasi-convex of the word hyperbolic G, then lambda H is less than lambda G. What did you say?
G would be not
Okay, fine.
Did they do that to you in your talk?
Yes.
Yes, that very thing.
Thank you.
You don't need it.
So you do genuinely need it. Thank you very much for that correction. Let's move on. So let's leave out that elementary thought and focus on the real thing. So what's the sketch of this? Well, there exists some element little g such that the group generated by H and little g is isomorphic to a free product, right, for some non-trivial element over here. And then because of this, hence, lambda H is strictly less than lambda of this free product, which is of course less than or equal to lambda G. So you just have to think through how the difference between H and the free product of H with some non-trivial element, and you'll find that there's an exponential difference between these two, owing to a kind of treeness of this freeness. Okay. Okay. So I would say that you saw from Dave's talk yesterday why we were curious about this. We needed to know that the hyperplanes had, the hyperplane stabilizers had lower growth than the group itself in a cubulation of, in some compact, in some compact Q complex, but with hyperbolic fundamental group. And we sort of, we didn't find it in the literature, and then we went and, did the dumb thing of sitting and working it out, and then we got all sorts of help from many, especially this guy, who sort of improved the results, and also probably the proof that we stumbled upon was first Samusetti. Huh? Excuse me?
Not pain because no proof that we see subset.
Pain. Okay. So yeah. So I don't even remember what our conclusions were. In any case, Pain. Spell the name for me.
P-E-I-G-L-E.
P-E-I.
E-I-G-L-E.
Okay. So in any case, The next thing that we were curious about after this was simple, I guess just an example. What we showed was that, obviously prodded by this observation here, that there exists a sequence of finitely generated subgroups HI contained in the free group of rank 2. These are infinite index subgroups, such that lambda HI converges to lambda F2. The growth rates of these infinite index finally generated subgroups converge to the growth rate of the group itself. So here, so X is going to be a bouquet of two circles, and we're epsilon is just the universal cover of X. Okay, we're doing our computations with respect to this metrization. So let's talk about this for a moment, because it's really this talk is just about a generalization of this. And I think the main point is really just to understand this is quite simple. So here's a sketch. For each I, let xi hat to x be base cover with girth, I don't know, really big, greater than or equal to 4i, g being 2i. Let yi be a subgraph be obtained by deleting, busting one edge, and then let hi be pi 1 of yi, and well, then lambda hi converges to 3.
Should I think of the xi hat as fine stuff?
Yeah, thank you. So then maybe I'll add that word. Okay, so the picture is like this. So you have some finite cover, okay, with relatively large girth. Girth is increasing as I is increasing. And then I take one edge and I remove it. Okay, so now I just have, maybe I won't redraw it, so here, it's gone. Okay, you even see where it's gone. Okay, and this is X okay, and now the picture in the universal cover well, you'll take a look at this pre-image. You'll look at the pre-image of this yellow busted edge inside of the universal cover. And what you get is, well, this edge got removed, and this edge got removed, and maybe this edge got removed, and maybe this edge got removed. Right? Those are the pre-images of that edge. And the yi tilde is just going to be this based tree that it's the component of this tree that you get when you remove all the yellow edges, the component that contains the base point. Okay? And computing the growth of hi is basically computing the growth of this tree that you get when you bust these yellow edges and prune. And, well, basically what happens is that any two of these yellow edges, so the bust edges, are far from each other. They're what, at distance greater than or equal to what, 4i or whatever, owing to the girth. Right? And basically, what happens is that you can imagine the worst case scenario, right, which is you kind of take every yellow edge and move it up, because they're appearing in sporadic positions over here from the viewpoint of the rooted tree. So you kind of round them, move them up slightly, you get an even, you move them up slightly, you get a smaller tree, right, whose growth will be, perhaps smaller, but it'll be lower bound. Right, so you move all of these edges up. So there'll be one over here, and one over here maybe, and one over here. So you move them up so that they're, appearing at maybe intervals of, cones of height I, one per cone, right? And they're, and then what? So you get a kind of smaller rounded up tree. Rounded up tree. And, well, we want to compute the growth of this rounded up tree is going to be less than or equal to the growth of the busted tree, the one corresponding to yi tilde. And, when you think of each of these, when you think of a cone, and you think of what's happening to a cone, and it has I steps, and you imagine such a cone, and then you say maybe, well, then I'm going to bust one edge leaving that cone. You can actually think in those terms instead, right? And so basically what you find is that the amount of stuff over here is like 3 to the I plus 1 minus 1, because you're just gonna remove this one vertex. You can throw that in the garbage. Okay, and well, so if you break this up by cones and then compute the growth, you'll see that the growth is approximately so what we find is that lambda hi is greater than or equal to well, let's see if I can get this right. The ith root of 3 to the I minus 1. That's a rough idea of what happens. And then as I gets larger and larger, you're getting closer and closer to 3. Okay? So you can kind of retrace these steps and see you'll be able to make a rigorous proof out of this. Not too much difficult. Okay. So so leads us to the to our definition that we're interested in. G has a growth gap if there exists epsilon strictly less than G. So G is now still acting on epsilon. It has a growth gap if there exists epsilon strictly less than the growth rate of G, such that the growth rate of any subgroup is strictly less, is less than or equal to epsilon. Right? And, well, you have to qualify which subgroups, because we know this is not going to be of any use when H is a finite index. So let's cut that down a little bit. So let's say whenever H is a finitely generated subgroup, of infinite index. Okay.
This is the difference between lambda G and lambda.
Yes, one of the.
So,
Oh, this is, that's
Here.
Sorry.
For those of you who
Oh, yeah.
get jet lagged,
There you go. Okay.
we add the missing step.
It's a big epsilon.
Oh, what
That's
am I
not to be
supposed to do?
small.
It's not a little epsilon.
Yeah.
I see. Oh, I'm so sorry.
Danny,
You're also keeping track of Saul's comments?
I'm not keeping track of Saul's comments, but I believe H quasiconvex.
Okay, now that's an excellent idea. Likewise, G has a quasi-convex growth gap, free growth gap, etc. So you can strengthen, we're going to hold on to this infinite index, right? But we will take, well, we can mess around with finite, with this adjective over here, with this condition, and look at different types of growth gaps, right? So, you know, if you like word hyperbolic groups, then a very natural thing would be to ask whether your word hyperbolic group has a growth gap with respect to its infinite index quasi-convex subgroups. Right? But you might also say you only care about free subgroups, and you might be curious about whether there's a free growth gap. And different people thinking about this over the years have considered different scenarios and reached interesting conclusions. So,
does this definition depend on the metric space in H1?
well, that's an excellent question. So let me address that in a moment. Let me first say that if G, so I'll get to that in a second. If G has sub exponential growth, something we already mentioned before, then G has no growth gap. In particular, if G is finite. Right, Jiakai and I spent a lot of time trying to make a philosophy of why when G is finite, then G has no growth gap. Right? And we reached the conclusion that the way to think about it is that no growth gap means that the supremum of growth of infinite index subgroups satisfying your conditions, maybe finally generated ones, the supremum, this is the supremum, I'll put a little box around it to draw your attention, the supremum over this class of growth rates should be equal to the growth rate of G. And, well, when G is finite, this is the empty set. And then, fortunately, so we get the supremum, in the finite case, the supremum of the empty set. Now we get into real fine points like that. It's equal to 1. Since growth rates are, well, inside of this partially ordered set right over here. Okay, so that was probably the high point of this talk. But we, we gave it some thought. I don't know if it was worth thinking about. Maybe you can also say it doesn't have a growth gap in that case. So that's fine with me. And maybe one more example is that, well, if you take a short exact sequence, where Q has sub-exponential growth. Then you can convince yourself that lambda n is equal to lambda g. And so, for instance, so using Rip's short exact sequence, which I know and love, we see that there exists small cancellation groups. With no growth gap. But of course, I didn't say they don't have a quasi-convex growth gap. I said they have no growth gap, right? Because I'm allowing any subgroups over here, and this subgroup N is a bad subgroup. Okay? Now, a foundational issue over here, which is way well over my head, is having a growth gap, of some type, right, over finally generated subgroups, or over the quasi-convex subgroups, or whatever, independent of your choice of proper co-compact action on epsilon, right? That's immediately led to that question. Beautiful question, and maybe subtle. Maybe it's a subtle problem. It's certainly one. It's a foundational point that I'm not that I'm not comfortable with. I guess my first reaction to it was, of course, and then I started writing down a proof, and of course, my proof was terribly wrong, and I found it to be slippery. So it's an interesting problem to attack, and maybe it's maybe you'll have the right viewpoint and you'll be able to explain it to us. And then, okay, so some more background. There's a lot of background. So in particular, e.g., is it independent of your choice of K-ligand? Were you asking a question?
Yeah. So you're restricted to finitely generating subgroups, but suppose you have an infinitely generated subgroup and you take larger and larger generating sets. Do you get that?
So I'm reluctant to consider infinitely generated subgroups because there are so many, and as soon as you have a quotient with sub-exponential growth, your infinitely generated subgroup is going to have the same growth rate. The kernel of that quotient is going to have the same growth rate as the original group. So
but you're allowing finitely generated subgroups. So if you keep adding on generators and you take the supremum, you get the growth for the.
No, you could let me think about that. You're saying, suppose that I keep adding more and more generators of, let's say, okay, let's think about that. If you have a finally generated group, okay, and you keep adding generators one at a time, right? So, eventually you get the whole group, right? So what are you asking?
Actually, this is about growth gaps, right?
Can we agree that that was a great interpretation of your question and that I can move on? Huh?
All right, we'll talk about it.
So there's some magnificent results here to tell you about. Corlette in '92 proved let G be quaternionic, hyperbolic lattice, or even there are many quaternionic hyperbolic lattices, different dimensions, or maybe a lonely one of the lattices in the lonely Jiakai Li octonions, or whatever they're called. Then G has a growth gap. Beautiful.
A finite generator.
Well, so let me see. If it's a lattice, does it?
Yeah.
It's you know, I'm not sure that he used finite generation. Richard, do you know?
I don't think so, no.
No, I don't think so. But it's true also for finally generated. Okay.
But I believe he used that the space is the appropriate hyperbolic space.
The metric that he's using is this metric right over here. So the epsilon is this is hyperbolic quaternionic hyperbolic space, etc. Okay, thank you. And then I mean this is we couldn't help hearing about this this result. You know, when we start to try to figure out where we had landed, we couldn't help but conjecture that if G is infinite and has property T, then G has a growth gap. Lo and behold, working sometimes a little bit before us and a little bit after us, and let's see, Dougal 17, Dougal Sharp, 16, proved that proved a growth gap for normal subgroups. Richard, is this were they manifolds in that case? Were they Lickler manifolds?
Yeah.
Yeah. And a little bit more recently, Coulomb, Dalbon, Sambucetti proved the growth gap for word hyperbolic. G, these are both with property T. And here, their results are with respect to either a Jiakai Li graph or with respect to a negatively curved manifold, the metric on negatively curved manifold universal cover. Blown away by this beautiful, beautiful theorem, sort of the most interesting case. One wonders what happens when you're not hyperbolic at this point. In other directions, sort of a positive direction, which I'm about to tell you a little more about, Phillips, Sarnak, stringing together a whole bunch of papers during the last 20 years, and Louis Bowen very recently showed that let Mn be hyperbolic. There's some restrictions on whether the dimension is even or whether it's closed or not, or whatever. Let's not worry about it. Let's just pretend it's all just hyperbolic manifolds of dimension 3 or more. They said there is no free quasiconvex growth gap. So there's a striking battle between the property T groups and the highly non-T groups that we stumbled onto. Yes?
So is it known that this is not a QI invariant? Is that?
It is. I don't believe that's not. I would suspect that having a growth gap, I would guess it's not. I mean, I think that there hasn't been enough effort in this topic yet, and I mean, there's just respect this problem over here. Yeah. So, right. And now let me state on the. Let me state what Jiakai and I did.
So in all these examples, the actions are also co-compact, or
Well, I think that for the examples that people, I think for these theorems, you mean, I think these are all co-compact. Richard, is that right for your work?
Convex co-compact.
Convex co-compact. Okay. So, what do you think? Should I be using my important time to give you all a little bit of schooling in how to erase blackboards? Maybe. There's still a few days left in the conference, so. Okay. I missed a spot. So, let X be a compact special cube complex, then its fundamental group, and epsilon is the universal cover of X using the taxicab metric, then G has no quasiconvex growth gap.
Is G still hyperbolic as well?
No, not necessarily. Not necessarily. So, I don't. Huh?
So this quasiconvex mean like cubically convex?
Yeah, quasiconvex means cubical convexity. That's right. Okay. Thank you for that. Right. So yeah, 20. Well, I just tried to remind myself that Jiakai was probably either 20 or 21 when we did this. He was a sophomore at McGill. Tough guy, huh? There are some McGill people here that can attest to that. He's a tough guy, right? So, it only took him a month to get to the point where he said, Donnie, I don't think you understand the proof. And then explained it to me. For my other collaborators, it usually takes them 2, 3, 4 months. So, give myself 1 minute extra. 1 minute of extra time, right? Is that okay?
Do I have a choice?
Can I have an extra minute for you guys?
Yes.
It isn't enough. So here's the idea is that of course what are we doing? We're generalizing this proof. That's all we're doing. The whole thing about special cube complexes is anything you do for a graph, you can do for a special cube complex. That's the whole idea. So this was just begging to be generalized. So you take your cube complex X, you let xi hat be a cover such that finite cover, yes, a finite cover such that the injectivity radius of each hyperplane, and hyperplanes play the role of edges, the injectivity radius of each hyperplane is large, let's say it's greater than 4i, whatever. So you have some giant finite cover. This is xi hat over here, and here's this hyperplane. Right? It could be a really big circle. I don't really care about that. But the point is that it's quite a distance to get from here to here. This is bigger than 4i. And then you let yi, you just remove the interior of that hyperplane, and then you do the same game. There's a tree which corresponds to the tree corresponds to a regular geodesic language. Actually, in this case, it actually associated to an automatic structure, although we don't care about that, but it happens to be associated to an automatic structure. And the tree, this language has the property that you travel through any hyperplane that you can travel through, you travel through it as quickly as you possibly can, right? Subject to some ordering of the hyperplanes. That's the way that the language is defined. And this sort of yellow hyperplanes that you knocked out end up corresponding to certain yellow edges that you knock out over here. And then the proof is just the same, except it's a lot harder. And the keywords are Frobenius. And I'll tell you one other thing, which is that it turned out that the Miller, the language, the regular language that we use, I apologize, I ran out of time, it turned out to be the inverse of the Hermiller-Meyer language for understanding automaticity of writing Artin groups. And otherwise, it's basically the same story. But the main thing is to understand, you just take a finite cover and remove a hyperplane, and it kind of looks almost like a finite subgroup. Right? And when you take a really, really big finite cover and remove just one little tiny bit of hyperplane, you're practically making almost no damage to the thing. You practically have almost the same growth rate as you can imagine, and you can prove it by messing around. Okay, I'll stop now. Sorry.
Any questions for that?
What part of the proof didn't you understand?
It depends on when I was chatting with him. I was confused about different things.
What's the?
I'm going to bear everything.
What's the tricky bit? What's the
None of it was tricky for Jiakai. Yeah.
It's clear that works in a hyperbolic case, or should work or something, but it seems a bit. Is there anything to say about what happens when you use
Hyperbolicity plays absolutely no role.
So what happens if you try to do this with a torus?
Oh, it's an excellent question. I should have ended the talk on time, and then we could have just gone to that question period, and then I would have just continued, right? That's the traditional way. And so,
Maybe literally mean the close because Z squared already has.
I know, but somehow.
I can still take advantage of that question. So, right, so here's there are two competing automatic structures for Z squared. There are many automatic structures, but the ones that one is most naturally led to, one of them is the Niblo-Reeves automatic structure, which generalizes to all compact cubic complexes. Right? And for that one, you start off at the base point, and you kind of go diagonally as far as you can, and then you proceed horizontally or vertically. Etc. And then a more straightforward automatic structure. It's a little less obvious, I think. It's pretty natural. This is really Gersten. It generalizes Gersten's short automatic structure for C4T4 small cancellation complexes. That's where they got it from. A more natural method might be to kind of travel as far as you can, say vertically, on your way to some point, and then go horizontally. So you led to a biconing. You guys are all, most of you are too young to have even heard those words. You led to a combing, right? I'm actually using a combing here. I'm too old to know what a combing is. Okay. So this is the other type of automatic structure that one is naturally led to. And this is the one that generalizes to Hermiller-Meyer. And you have this language, and the language corresponds to these yellow paths, and then you fold up the language and you get a tree. And then, of course, like you said, for Z squared, there isn't any growth rate to worry about. But I took advantage of, I exploited the opportunity to sort of tell people a little bit about the regular languages involved. You need some type of counting device, right? And the growth is related to, we think of the growth as being the growth rate of a tree that's living inside, right? Kind of spanning tree, sort of. We're counting vertices in a spanning tree, and it has this nice structure which makes it a little bit easier to do the counting.
Any other questions?
Yes. Could you explain the role of the growth in this theorem? Recently learned about this theorem.
So what happens is that you end up with the role. So what happened in this proof over here, the free group, was that we were able to. There's a kind of homogeneity over here, right? Because it was every vertex had valence 4. Right? But in general, this tree which is associated to this automatic structure, it's not perfectly homogeneous. Right? But it will have the property, when you set things up properly, it will have the property that that any cone type for this automatic structure has every other cone type as a descendant. So, when you look at any little subtree over here, you could find inside of it other cone, every other type of cone living inside. And what that ends up corresponding to is a irreducibility or strong connectivity of the associated automaton. And then Frobenius is able to tell you growth rates of such things using eigenvalues. So that's as much as I'll say.
Okay, if you have any other questions, you can ask during the break. Actually, let's come back at 25 after.
Great,
Thanks,
Mr.
Dr.
Hansen.